Hi class. In this video I want to review some basics of curvilinear coordinates that we use in mathematical physics. The usual Cartesian coordinate system in 3 dimensions, x, y, and z, is a convenient basis, and it's the intuitive one that we often use in a lot of our calculations. However, a lot of systems have some kind of rotational symmetry. And if that's the case, then Cartesian coordinates aren't a particularly convenient coordinate system to use, because under rotations, what we mean by x, y, and z get interchanged in two coordinate systems related by a rotation. So in this case, it's often better to use polar, cylindrical, or spherical coordinates, and I wanted to review those for you today. Let's start with polar coordinates. Polar coordinates are coordinates in 2 dimensions, where instead of the x and y axis in the Cartesian sense, for any point r, we define it by its radial distance from the origin r and the angle theta, which the radius vector makes with the x-axis. So the coordinate transformation that relates x and y, the x and y coordinates of the position we're at, to r and theta, our x is r cosine theta and y is r sine theta, which we can invert to say r is the square root of x squared plus y squared, and theta is the arctangent of y over x. Now, the arctangent means we actually have to define the range of the arctangent, what set of angles we're actually going to consider, and there are 2 common sets that are considered. In the mathematics literature, it's often common to use theta going from 0 to 2 pi. In physics, we often are interested in a representation which theta is continuous at the origin, so we take theta as going from minus pi to pi, so there's no discontinuity in what we mean by the angle at theta equals 0. But this is a convention. You could use any other convention, but these are the 2 that are most commonly found. One important thing that we emphasized when we talked about vectors is that corresponding to this new coordinate system r and theta, there's a new set of basis vectors that I'm going to call er hat and e theta hat. I think in my previous lecture I called it r hat and theta hat. But er hat is just a unit vector in the radial direction. E theta hat is a unit vector in the angular direction. And one big difference between the basis vectors in polar coordinates and the basis vectors in Cartesian coordinates is that, in fact, this er hat and e theta hat depend on where you are. Up here on the y-axis, er hat points in the positive y direction, and the x-axis, if you were to point on the x-axis, er hat points in the positive x direction instead. So er hat and e theta hat are actually vector fields. At every point in space, here in this 2-dimensional space, there's a different set of basis vectors, er hat and e theta hat. Now, polar coordinates are useful if you have a 2-dimensional situation in which there's a rotational symmetry around the origin. So, for example, in planetary motion, where we're talking about a particle, a planet that's being attracted towards a center of gravity, the sun, roughly speaking, then we would put the sun at the origin of the coordinate system, and we would describe the motion of the planet. Because of conservation of angular momentum, the motion of the planet is confined to a plane. We define that motion in terms of its radial coordinate r as a function of time and the coordinate theta as a function of time. There's a generalization of polar coordinates to 3 dimensions where we just put the z-axis on like this, and we use polar coordinates in the plane, and we tack on the z-coordinates. So the basis vector change, or sorry, the coordinate transformation change is just the polar coordinate transformation change plus the z coordinate. Here, there's going to be basis vectors er hat, e theta hat, which are parallel to the xy plane, and ez hat, which is perpendicular to the xy plane. And this is useful for a 3-dimensional situation in which we have cylindrical symmetry. One last thing I should mention before we talk about spherical coordinates on the next slide is that these coordinate transformations are going to be vital to us. They're going to allow us to say whenever we can describe something, say a physical law, in Cartesian coordinates in terms of x, y, and z, these transformations will then tell us how we can describe those physical laws in polar coordinates, say here, or into cylindrical coordinates. The last of the classic coordinate systems that we're going to be using frequently are spherical coordinates. And here we take the x, y, and the z rectangular coordinates, and for an arbitrary point out here, we think about the radial distance from the origin, r. So in a sense, this is a more complete generalization of polar coordinates. But now we define the direction of this radial vector in terms of 2 angles, theta, the colatitude, the angle made with the z-axis out to the radial direction r, and phi, the azimuthal angle, which is defined as the angle in the xy plane of the projection of this vector down to the xy plane. Now, it's important to remember that even though we use r and theta here in spherical coordinates, they have a different meaning than they do in polar or cylindrical coordinates. So you have to specify what coordinate system you're using, and it's not always implicit. If you see r, theta, and phi, it almost always implies that you're using spherical coordinates. Theta here is like the colatitude, if you want, instead of the latitude in geography. This is the angle from the North Pole, if you want, down to where you are on the surface of the Earth instead of from the equator up. And phi is very much analogous to the longitude in geography. In mathematics, you'll often see a definition where theta is the latitude instead of the colatitude, but I'm using the description that's most common in physics. Corresponding to these radial and angular directions, there are unit vectors. Er hat, again, is defined as the unit vector in the direction of increasing r, and similarly, e theta hat and e phi hat are the unit vectors in the direction of increasing theta and increasing phi. And you can compute what er hat, e theta hat, and e phi hat, and we will, are in terms of I hat, j hat, and k hat. The fundamental coordinate transformation can be written as x is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. Again, here it's crucial that we've used the definition of theta as colatitude. You can work out what the inverse relationships are, which define r, theta, and phi in terms of x, y, and z. But this is the combination which we'll most often use it. Spherical coordinates are particularly useful for problems with spherical symmetry, and probably the most famous example of such a situation is the hydrogen atom, where we think of the proton as being infinite mass and of positive charge. We put that at the origin of our coordinate system. Then the potential felt by an electron at some distance r depends only on the radial distance and doesn't depend on these angular coordinates at all. The potential is minus e squared over r. And you can see that if I were to write this potential in terms of rectangular coordinates x, y, and z, the potential would look much more complicated.